looked back at any of the recordings? Oh, cool. Then I will continue to try to remember and forget sometimes. So, the point of today's lecture is Archimedes' property, which is a thing that's the existence of suprema, that completeness buys you. So Archimedes' principle is like listed right there at the top at the end of the dash. The set of all natural numbers is not bounded above, which seems like intuitively obvious, right? When you draw the number lines, yeah, the natural numbers go on forever. But if you drop the completeness axiom, you can construct an ordered field in which the natural numbers are bounded above. You can construct a field where there's like something that maybe you would want to call infinity, and is still a field. And I'll leave it to you to maybe think on that. If you want to keep thinking on it hard, then like I'll give you a name of the field and you can check all the conditions. So let's start by defining the natural numbers. And like, you know what the natural numbers should be. It's 1, 2, 3, 4. But let's give a definition in terms of what the real numbers are. So, definition. The set of natural numbers denoted /mathbbn is the subset of the interval from 1 to infinity, including 1, because 1's a natural number, defined recursively as follows. The multiplicative unit 1 is a natural number. So that's like the base case in this inductive definition. For every real number n bigger than or equal to 1, n is a natural number if and only if n plus 1 is a natural number, yeah. So 1 is a natural number, that's true if and only if 1 plus 1. So 2 is a natural number. 2 is a natural number if and only if 3 is a natural number. And so on. Does that feel like a definition? Yeah. And I think to get it right, this should actually be a bigger than 0. Because then what would you say? Well, 0.5 is not a natural number because it's less than 1. So it's not a sub in that subset. Oh, that means 1.5 is not a natural number, which you knew it wasn't. So now the definition, I think, is good enough. All right, so what I want to do, we have the set defined now. It's the set containing 1, it contains 1, so it contains 2, it contains 2, so it contains 3. Let's prove some things about this set. And let's start with Archimedes' property. Archimedes' property says n, as a subset of the real numbers, has no upper bound. And let's try to come up with a proof. So the proof's going to be like sneaky, but let's try to motivate it some. So this is all about completeness. Completeness tells you something about sets that do have upper bounds. I want to show that n doesn't have an upper bound. So that sounds like a proof by contradiction might be a reasonable plan. Because then I would know that it does have an upper bound, and I could use completeness. So let's do that. So let's suppose, for the sake of contradiction, that n is bounded above. All right, cool. It has an upper bound then. What does completeness tell you once you know the natural numbers have an upper bound? What do you know about every set that's non-empty and has an upper bound? It has a supremum? Yeah. And that's it, right? So the point of having this completeness axiom is whenever you're in a situation where you know two things, X is not the empty set if you know X is non-empty and X is bounded above, then you know the supremum of X exists. That's not terribly legible, but I said it all. So as soon as you have a set that's non-empty and bounded above, you can refer to its supremum, and you don't need to know what the supremum is. You know it exists. In fact, here you can't know what the supremum of the natural numbers is, because I think we're going to get a contradiction. So, By completeness, n has a supremum. I am going to call it S for supremum. If you're the type of person who likes to talk about LUB, then I don't know, I guess maybe you'd want to call it U. I'm going to call it S, doesn't matter. So let's talk through a few things. S is the least upper bound. Could S minus 1 be an upper bound? No, why not?
Well, because S is the least upper bound.
Yeah. S is the least upper bound, so something less than S can't be the least upper bound, otherwise S wouldn't have been the least upper bound. S minus 1 is less than S, and S is the least upper bound. Where here I wrote that in caps in order to call your attention to it. I'm using the leastness of it. So S minus 1 is not an upper bound. If S minus 1 is not an upper bound, what does that buy you? Yeah.
That doesn't exist in greater than this maximum.
Yeah, in fact, strictly greater than. There exists some element of the natural numbers such that little n is strictly bigger than S minus 1. And I don't know, how people want like the reminder of how to do the logical calculus to see that that's the right thing to write? How many people want that? Cool, I'm going to do it anyway because I want to do it. Why did I ask then? So, you know that S minus 1 is not an upper bound. So this is, again, something out in the margin that, like, wouldn't be in your proof. So you know that not S minus 1 is an upper bound. So you know not for all n in n, n is less than or equal to S minus 1. Because that's the definition of what it means to be an upper bound. Oh, cool. So now you know how to negate statements, right? That must mean there exists an n in n for which the conclusion is false. For which that is false. So little n is bigger than S minus 1. The ST is an abbreviation for so that or such that. Neato. All right, so let's see what we have right now. S is the supremum, but I have a natural number n so that little n is bigger than S minus 1. And I know there's like stuff written now. But let's see, little n is bigger than S minus 1, and S is the supremum. I want to get a contradiction somehow. What seems useful? Yeah.
There's a natural number that's bigger than S.
There's going to be a natural number bigger than S. And in fact, what is that natural number? N plus 1. So let's add 1 to both sides and get that. N plus 1 is bigger than S. And why? Well, since little n is in the natural numbers, so is n plus 1, by definition, 2.6.1. Oh wait, but that means that S isn't an upper bound. The supremum is the least upper bound, so it's an upper bound. So there's a contradiction. If the set of natural numbers has an upper bound, then it has a least upper bound. Oh, but that least upper bound can't be an upper bound. That's bad. So the assumption we made for the sake of contradiction must be false. What assumption did we make? We assumed that n is bounded above, so we conclude that n is not bounded above. That feel pretty good? And there's like the prototypical use of the supremum of completeness. As soon as you know that something is bounded above, you know that its supremum exists. You don't know what the supremum is, but you know that it exists. In this case, you know that it exists, and you show that it doesn't exist. And there's your contradiction. Does that feel pretty good? Nice. So what all of this is going to be some variations on that theme, culminating with the following result. So I'm flashing all the way up here because like this is the goal I have for the rest of today. The density of the rational numbers. For any real numbers x and y with x less than y, there is a rational number in between x and y. That's something that like should be true, right? Some people in here are taking the topology class right now, right? Who's taking topology? Cool, so I think you've been talking about the density of Q a few times in the topology class. And like never rigorously because it doesn't belong in that class. We will here, we're going to actually prove that fact. All right. And we're going to build towards it one piece at a time. And I guess maybe I've like spoiled this question a little bit. So that definition 2.6.1, you could make sense of that in any field. Right, what do you need to make sense of 2.6.1? You need 1 to be in there. Well, 1's in any field. You need to be able to make sense of intervals, so you need inequality. So I guess you need an ordered field. And then you can run exactly definition 2.6.1. So the natural numbers sit inside of every ordered field. Do you think that you could, well, I spoiled this a little bit, but do you think there should exist an ordered field where like the natural numbers do have an upper bound? I guess you could imagine like trying to construct it. Like, let's suppose it had a supremum. I guess you would want to call that something like infinity. And it's not like infinity, it's like an element of the field. So that'd mean you'd need an inverse to infinity. So you need an infinity inverse, 1 over infinity. It shouldn't be 0 either. You also need infinity plus infinity. You also need to divide by things. It's like, I think if you use that as a starting point, like mess around some, you'll see a candidate. But the point of this class isn't that candidate. There is such a field. And you can come up with it by thinking of that. But like, this is about the real analysis. We want to study the real numbers. So let's build more things. Let's talk about the integers. So the integers, mat BBZ, is defined to be the set of natural numbers together with 0, together with all additive inverses of natural numbers. Does that seem like the right definition for Z? Yeah, I think so. And I'll use this notation sometimes in the class, colon equals for, I'm defining this to be equal to that. If you like, that's notation borrowed from a lot of computer science. When you want to set a definition, I'm not testing if it's equal, I'm setting Z to mean that set. The claim is that set is not bounded above and is not bounded below. So let's try to come up with like, before we flip to the next page and actually give the proof, like what seems like some useful ideas. Let's try to sketch something out. So I guess I want to prove 2 things. I need to prove it's not bounded above and it's not bounded below. So, can you make progress on either of those 2 goals? Let's see, it's labeled as a corollary. That's telling you something about how the proof should go. It should be a consequence of the thing that we just proved. We just proved that naturals aren't bounded above. So, what can you do with that? Yeah.
It's just the natural numbers, but like you're extending it to include numbers below 0.
Mm-hmm.
So it doesn't change the fact that it doesn't have an upper.
Nice. If the set did have an upper bound, then that thing would also be an upper bound on n. If Z has an upper bound, that upper bound is an upper bound on n. That's a contradiction, so the if part of that if has to be false. I like that. That gets you the upper bound statement. Maybe we could pull something off with lower bounds too, like using the same logic. So let's see. So this is all like scratch walky stuff. If L is a lower bound on Z, then let's try to do some stuff. If I had a lower bound on the set of all integers, what could you do? Yeah.
You could multiply everything by a negative and get the S, the supreme number.
Cool. So that would be like a negative L, and then what do you want to do with it?
That would like translate to a supreme number of N, which you know doesn't exist.
Yeah, and supremum I think is too strong, and like, I bet you could do something with supremum, because you could say like, oh, if L was the infimum, minus L would be the supremum. But then you have to prove that, and I think it's easier to do this. If L is a lower bound on Z, then minus L is an upper bound on N. Does that get you the same contradiction? Nice. Well then, we have the sketch of proof. Let's just put it into words on the next page. Maybe that claim needs some justifying, but we know how to show something's an upper bound, and it should be pretty quick. So let's try to do it. So let's proceed by contradiction. Suppose that Z is bounded above, let U be an upper bound. Explain why U is an upper bound on N. And I don't know, like we didn't explain why on the previous page, but explain why. Why should this U, which is an upper bound on Z, also be an upper bound on N? Well, you have the idea, so like, what would you want the justification to be?
I don't know if it's right, but I feel like N is a subset of Z.
Yeah.
Would still, like, is that enough?
I don't think we've formally proven that upper bounds behave nicely under subsets. So, if you wanted to prove the following lemma, then you could use that. Oh, yeah. Well, the thing you just claimed, we could prove that lemma. In fact, now that I see that lemma written down, maybe I'll remind you that like there are these benchmarks that I want to ask about ordered fields. That seems like an ordered field question that's pretty accessible. But instead of proving that, let's actually just prove that lemma in this case. If you want to show U as an upper bound on N, well, we just need to go from this to that. That's what it means to be an upper bound. So let's use this like subsettingness argument. So if N is an element of the natural numbers, convince me that N is less than or equal to U. There's the definition of Z, and U is an upper bound on that. So, is every natural number an integer? Yeah, right, because the integers are a union of the natural numbers or something. Okay. So for every n and n is in Z. And I assume that U is an upper bound on Z. So what do I get? Yeah, but I guess in particular it's bigger than or equal to this little n. So n is less than or equal to u as u is an upper bound on z by assumption. And that was just the goal, and I didn't use all the space. That feel pretty okay? Does that prove it's an upper bound? On n? Does that prove that u is an upper bound on n? Yeah. I considered anything in n, I got n to be less than or equal to u. That's what it means to be an upper bound. That n doesn't look very good. All right, so we have an upper bound on z. Is that a contradiction? Better be. Yeah, we know it doesn't have any upper bounds by the theorem we just proved. Oh. This contradicts that theorem, theorem 2.6.2. All right, so z isn't bounded above. Let's also show it's not bounded below by using the same sort of argument. Suppose that z is bounded below and that L is a lower bound. We shall explain why minus L is an upper bound. Because that's like the same idea as you told me. Multiply by -1 and see what happens. All right. So let's consider any natural number n. Minus n, is that an integer? Yeah, the integers contain additive inverses of natural numbers. Since L is a lower bound on z, what conclusion can you make? Well, you can conclude that L is less than or equal to, and now you can say any element of z that you want. What element of z would you want to put there? Could put an n there. I'm going to leave myself space because that's not what I actually want to put there. By multiplying both sides of the inequality by -1, I get L to be, minus L, to be bigger than or equal to -n. Oh, that's no good. That doesn't get me an upper bound on the naturals. That gets me an upper bound on negative the naturals.
So you need the negative side.
Yeah, and that's something that'll happen like a few times in this class. We'll compose a proof. We'll see something that we want to tweak midway through the proof to like get the contradiction we want. And we'll like make that tweak and then fix the proof. And when you do that on your own, maybe that means you have to like rewrite everything, but we don't have time to do that live in class. And happily, like it was a matter of erasing one thing. Cool. So, negative L is bigger than or equal to n for all n in n. So negative L is an upper bound on n, again, contradicting Archimedes' principle. Cool. Feeling good? All right, let's keep on going. So, the next couple of results are all things that are like intuitively true and useful. And the reason I've included them is because I'm going to use those results in the proof of the density of Q. So, let's do it. Here's the first. If A and B are real numbers, and A is positive, then there is a natural number n so that A times n is strictly bigger than B. So what does this say? This says something like you can multiply a positive number by a big enough natural number to get bigger than any number you like. That's intuitively what that says. If I give you two numbers and you know that A is positive, then you can multiply about that a by a natural number. It doesn't say anything about it being really big, but intuitively that n should be really big. So that you've now exceeded b. And let's see, I think I want to do two cases. So let's let a and b be real numbers, and let's assume that a is bigger than 0. So that's just like the setup. Those are the givens in the theorem. For the sake of contradiction, let's assume that for every natural number n, a times n, let's see, we want it to be bigger than b for some n. So I guess I get to assume that it's less than or equal to. So let's see, right now I have off in the margins a times n less than or equal to b for all n. I also know that a is bigger than 0. So there's what we have. A times n is less than or equal to b for all n. A is bigger than 0. And remember, we have Archimedes' property. So what seems useful now? I guess there's stuff going. Yeah.
We could say, like, if we could say B is an upper bound, then that would contradict 2.6.2 or whatever.
Yeah, so if we could just get b to be an upper bound, there would be a contradiction. So that would mean b to be bigger than or equal to every natural number n. Well, I know there's an a next to those n's. Can we get the a not to be next to those n's? Yeah, what would you do to do that?
We'll multiply its inequality by 8.
Yeah, so divide by a. Is a inverse still positive? Yep, you've even proved that in like some homework that's maybe due this coming week, this coming Friday. And it is less than or equal to a b inverse, nope, b a inverse or b over a. Which do you prefer? It's the same thing either way, right? Okay. I don't have a preference. That's why I was asking. It wasn't a trick question. Ooh, does that buy me an upper bound? Yeah. I now have a single thing that's bigger than every natural number, b times a inverse. That's natural number on n. I get another contradiction, so the thing I assume for the sake of contradiction must be false. Cool. So all of these have been like the exact same thing over and over again, just like do something to get a contradiction of Archimedes' property. Corollary 2.6.6 is the same thing again. It says that the least upper bound of the set of all reciprocals of 1 over n is 0. And the proof is going to be super similar. I guess first you'll need to convince yourself that 0 is a lower bound. Oh, but that seems pretty obvious. 0 is less than 1 over n for every natural number n. Yeah, convince yourself of that. To get it to be the least upper bound, suppose it won't and try to contradict Archimedes' property. So the last thing, which I'll prove, which again gets called Archimedes' property sometimes, says the following. If I give you any integer z, nope, any real number z, there is an integer somewhere in between z and z plus 1. Does that seem like another thing that should be true? In fact, like you kind of already have a name for that natural number. It's like the law of z plus 1, I think. If you take z plus 1 and round it down, you get an integer, and that integer is in that range. So I feel like this claim is showing that the floor function exists. Let's prove it. So, to do it, let's sketch it out first. We need to find a natural number n satisfying two inequalities. Nope, we need to find an integer satisfying those two inequalities. So let's start with an outline. So I need two things to happen. Z needs to be less than n, and n needs to be less than or equal to z plus 1 simultaneously. Let's see, if you only wanted an integer that's less than or equal to z plus 1, all that says is like you need z plus 1 to not be a lower bound on the naturals, on the integers. Oh, but you know that they don't have an upper bound, so z plus 1 can't be such a lower bound. So there's some natural number less than or equal to z plus 1. I think if you take the biggest natural number less than or equal to z plus 1, you'll win. So that's like a supremum kind of thing. So there's like the overarching strategy that we're going to use. Let's try to actually do it now. I feel like I'm going a bit slow to make it where I want. No, I'm okay. I got 1 page left in 10 minutes, maybe. All right, so let's try to prove it. So, I want to prove something about every real number z, so I better start by considering any real number z. Based on that intuition, let's start by considering this set. Let's set A to be the set of all natural numbers which are less than or equal to z plus 1. Explain why A is non-empty. As a starting point, explain why z plus 1 is not an upper bound on z. So let's start with this. Why is z, little z, plus 1 not an upper bound on the set of integers? Yeah, there isn't one. Or lower bound, I guess, whatever. Z has no lower bound, so z plus 1 cannot be a lower bound. Cool, that's nice. Oh, but what was my goal? A is not empty, so let's carry on from there. Since z is not not a lower bound, there must be something in the set z that's bigger than this variable little z. So there is some n in the integers with n less than z plus 1. Because you know z plus 1 isn't a lower bound, there's something lower than it. Cool. That feel good so far? Oh, but that means that this n satisfies all of the definitions of what it means to be an A. This n is in A, so A is not the empty set. All right, so I didn't give myself enough space to actually write on that, but I think that's okay. Explain why z plus 1 is an upper bound on the set big A. Well, explain. What does it mean to be an upper bound on a set?
Anything in the set is less than or equal to the.
Nice. So let's consider any, I don't know, I'll say A because little a is like a big A. Consider any little a in the set big A. Then what do you know about that little a by the definition of big A?
It's less than z plus 1.
Then A is less than or equal to, because it's less than or equal to there, z plus 1 by the very definition of big A. Oh, so big A is an upper bound by the very definition of big A. Right? That was like a truism almost. All right, so this set A is non-empty, has an upper bound, so A has a supremum. Let's let S be the supremum of A. As soon as you get a set to be non-empty and bounded above, you should take its supremum. That's like the thing you should do. If you're not doing that, then you're not doing analysis, you're doing something else. Not that that's bad, but like this is an analysis class. All right, so let's play the same game. S minus 1, is that an upper bound? No, it's less than the least upper bound. And so, that means S minus 1 is not an upper bound, so there's some n in A, so that n upper bound is not an upper bound, is bigger than s minus 1. Feel good so far? And we'll be coming to a conclusion pretty quick. And the conclusion will, like, give us what we want. As n is in A, we can conclude from the definition of A two things. N is in N is in Z, and n is less than or equal to z plus 1. With me so far? All right. Let's see. If I add 1 to both sides of this, s is now less than n plus 1. So s is less than n plus 1, and s is an upper bound on the set big A, so n plus 1 can't be in big A? Well, n plus 1 is certainly a natural number, though. So that means that it must fail this condition. So it must be that n plus 1 is bigger than z plus 1. Otherwise, it would be in the set big A. And this might seem like we're just doing random things, but we actually have everything we need now. Let's remember the goal. That was the goal. So let's just see if we have those things. Do we have something that says that z is less than n? Basically, we have that. And so, z is less than n by subtracting 1 from both sides. Do we also have n is less than or equal to z plus 1? By that. So we have now seen that n is less than z, is less than or equal to z plus 1. So we're done.
Z less than n less than s plus 1.
That better be what I mean. So I've talked myself in a loop. So now I'm scared. Do I actually have something that says that z is less than n? I do. Okay, so I did just write it down incorrectly. Z is less than n. I also have n is less than or equal to z plus 1. Cool. And so there's something really dangerous when you're doing math that I do all the time in this class. I write something down and then I walk away from it and I don't look at it. That makes it really easy to make that particular screw up. Happily, no one does their homework that way, right? No one goes to an empty room and tries to talk through everything like they're talking to someone without looking at the paper. So that's a really bad idea. Don't do that. It's fine to talk to someone else about the math you're doing, but don't do it like you're presenting it. Unless you have it done. Then you can present it. All right, last thing. The density of the rational numbers in 2 minutes. Yeah, we can probably manage. Because this is going to just put together the things that we already have. So, for every real number x less than y, there's some q such that x is less than q is less than y. So, let's walk towards the proof by starting with the motivation. So maybe we won't get to the actual proof. So what's a rational number? Something like a over b. So I want x less than a over b less than y. I want something that looks like that. I may as well assume that b is positive. The denominator for a rational number should just be taken to be positive by assumption. So I can multiply b to everything in sight. So that means I need bx less than a less than by. And that a now needs to be an integer. So what I need to show is that if I have a bx and a by, and I multiply them by something big enough, I can find a rational number in between. Do we have a result that just says you can do basically that? Kinda. So what can you do? You can definitely, well, what I was doing was dangerous there. I was trying to sketch a proof that has lots of moving parts really quickly without being sure of everything that's going to happen. So in reality, what I'm going to study is something about y minus x. That's something that I know is positive, right? So that means I can definitely multiply that by a natural number, which I guess is like the b, to get as big as I want. So I can pick b big enough so that b times y minus x is like bigger than 1. Yeah, now we're cooking. So that means by is bigger than bx plus 1. Well, that gap from bx to bx plus 1, that's big enough I can find a natural number in between them by the thing we just proved. There's the natural number a that we needed to find. Now we have a sketch, and I'm out of time, so we'll have to like regenerate the sketch at the start of Friday. So in fact, here's what I might suggest you do. Take that idea. We're going to like scale x minus y so it's really big. That means by is bigger than bx plus 1. Find a natural number between bx and bx plus 1 and show that you can now wrap everything back up to produce the rational number you wanted. Groovy. So I'm going to stop because we're all packed and I'm over time. I hope you all enjoy your lunch. I have my office hour at 1 o'clock today. Feel free to come on by. Oh, and don't forget that I'm going to ask you what the supremum, what completeness means again. Or, it's fine if you do forget that, just remember what completeness means.